In this video, I'm going to introduce briefly the fully homomorphic encryption scheme. In particular, I will introduce how the FAG techniques gradually developed over the past decade, and then I will get you some understanding of the real-world performance of FAG. And finally, I want to showcase some real-world applications where that fully homomorphic encryption could be useful.
The starting of fully homomorphic encryption was back in a paper published in the year 1978. So that problem now is called the lone company problem. Is that we have two parties, Alice and Bob. Now Alice has her own data and she wants to know her income in the next month, and Bob can help him to compute this value because he is a data analyst. So now we assume that Bob can compute the next month's income as a function f. However, Alice does not want to reveal to Bob her own private data. So in this way, Alice encrypts her data and send it to Bob. Now Bob has some cipher tags which he does not know the private data. Somehow, Bob can still compute on this encrypted data and get an encrypted F data. So after Alice receives this encrypted result, and she locally decrypts the result and get her next month's income. So in that paper, this idea was called privacy homomorphism, and nowadays we call it homomorphic encryption. So homomorphic encryption actually is a two-party computation and has the optimum rounds, that is 2 rounds computation, and the communication overhead is also optimum, that is proportional to the size of the input plus the size of output. Before introducing the details of fully homomorphic encryption, I want to introduce a very important concept called learning with errors. So the LWE problem is described as for any polynomial time-bounded distinguisher D, and I generate randomly a vector A, and I compute B as inner product of A and some secret vector S plus an error term E, and this computed B is indistinguishable from a random generated B. Based on this LWE assumption, we can easily construct a secret key scheme, and the key generation algorithm is simply generated a secret vector S randomly. And to encrypt a message X, I first generate a random vector A and compute B as an LWE sample as we have done in the LWE assumption, plus the message times a scaling factor. And now I call this output is an LWE sample, LWEX. And to decrypt this LWE sample, I simply perform a linear computation, is that B minus the inner product of A and the secret key S, and this returns me X times the scaling factor plus E, and I denote it as an inverse LWE sample. And when we reach this point, we can compute a simple rounding operation to retrieve the message X. So here is a graph illustrating the decryption algorithm. So by performing the linear operation, we get the inverse LWE as X times scaling factor Q, that is Q over 2, plus the error term, the small error term E. And now I suppose this message is just a 1-bit information. it is either 0 or 1. So if it is 1, then this value should be fluctuating around q over 2. And if it is 0, it is fluctuating around the value of 0. So anyway, we can still distinguish these two distributions, and by the rounding operation we have introduced in the algorithm, we can finally retrieve the bit message x. So in this talk, I will use over and over again the notation LWEX as the LWE encryption. However, the LWE encryption is not efficient. In practice, we use its ring variant called ring LWE encryption. So almost as same as the LW assumption, the ring LW assumption is like I generate a random polynomial A from the ring RQ. Remember, in the LWE assumption, we generate a random vector A. And also a secret S randomly from a distribution, and usually distribution is like a small distribution, and a error term E from the same small distribution chi. And now we compute the ring of W sample as A times S plus E. And the ring of W assumption says that this ring of W sample is indistinguishable from a random A and B, where both A and B are a random polynomials in the ring RQ. I'll put it another way. The ring of W sample can be viewed in the matrix form as shown in this formula. And this shows the ring of W sample is essentially a batch of LW samples under the same secret key S. And this naturally introduced an homomorphic encryption operation called the sample extraction, which can extract the constant term from the ring of W encryption, that is, which returns an LW encryption of the constant term x0. Now I denote as the red vector A prime. This A prime is essentially A0 minus A n minus 1, blah blah, until minus A1. And this S is our secret key, shown as S0, S1, up to Sn minus 1. Now, after introducing the ring of W encryption, we can talk about and discuss the homomorphic addition and the multiplication. So the addition is very easy. It's just a straightforward vector addition. Is that if A0, B0 is an encryption of M0, and A1, B1 is an encryption of message M1, should be M1. And I do the addition. This directly returns me an encryption of M0 plus M1. But the multiplication is not that obvious. There's no straightforward way we can do that. However, if we interpret the ring of W encryption as a degree 2 polynomial, as for example, CTI is the ring of W encryption, and it has two elements. Now CTI0 and CTI1, now I represent it as a polynomial. Now I perform the polynomial multiplications for CT1 and CT2, and returns me a degree 2 polynomial as ct10 times ct20 plus the cross term times x plus ct1 1 times ct2 1 times x squared. Now if we evaluating this degree 2 polynomial at x equals s, and this returns me essentially the message m1 times m2. Or formally, I claim that if I evaluate ct1 times ct2 at this point, and I will immediately have m1 times m2 with some extra rounding operation. But now the problem is that before we do the multiplication, ct1, ct2 both are degree 1 polynomials. After the polynomial multiplication, this new polynomial is a degree 2 polynomial. In other words, the ciphertext size expands. And now let's repeat our problem here. After we do the polynomial multiplication, we get like degree 2 polynomial. So the coefficients of the polynomial is like C0 prime, C0 prime, C1 prime, and C2 prime. And we try to reduce the size to the normal polynomial, normal degree 1 polynomial as C0 and C1 under the same secret key. Is that we hope that this formula holds that C0 prime plus C1 prime s plus C2 prime s squared is almost equal to C0 plus C1s. And this reduction is realized by we now call relinearization technique, which was invented in this BFV paper. And nowadays we call the BFV scheme as the representative of the second generation of FHE. So the algorithm is simple. Which we first invoke the relinearization key generation algorithm. I input the secret s and s squared. I got essentially an encryption of s and s squared, and denote as the RLK, the relinearization key. And now I perform, now we call the relinearized algorithm. We can reduce the size, the degree 2 polynomial into a degree 1 polynomial as C0 and C1. And the relationship between C0, C1, and C0 prime, C1 prime, C2 prime holds as shown in this formula. Now we finally introduce how we do the multiplication. Is that the BFV MAL algorithm. I give you an encryption of the message M0, an encryption of the message M1, and I also give you the relinearization key. And we can perform the multiplication in 3 steps. In step 1, we do in the polynomial multiplication we have introduced. So we have now we have a like degree 2 polynomial. Then we do the rounding on this polynomial 2 degree, as shown here. And finally, we invoke the relinearized algorithm to reduce these 3 coefficients into 2 coefficients. Now this one is essentially an encryption of the message M0 times M1. So after introducing the homomorphic addition and the multiplication, we already construct so-called leveled homomorphic encryption. So in the leveled homomorphic encryption, if you tell me how deep multiplications you want to go, then I will set up the FHE parameter and construct the FHE scheme for you. But now it brings naturally another question, is that if I don't tell you how many multiplications, how deep multiplications I want to go, but I still want you to construct a fully homomorphic encryption which supports unlimited numbers of multiplications. Is that still feasible? Now let's try to understand the difficulty to perform unlimited number of multiplications. So when we're doing the homomorphic operations like addition and multiplication, the noise inside the ciphertext gradually increases, and at some level, this noise is above the threshold, which means we can no longer decrypt the ciphertext correctly. A natural idea is that if we can reduce the noise back to normal, then we can again perform more homomorphic operations. And Gentry's bootstrapping idea essentially solves this problem, and it basically says if we can somehow homomorphically perform the decryption algorithm, then we will always be able to do unlimited number of multiplications homomorphically. So this bootstrapping theorem says that if a homomorphic encryption epsilon can support like depth D circuit, which means it can support the multiplicative depth to be the value of D, and very likely its decryption algorithm is relative simple that can be tolerated by this homomorphic encryption, then this homomorphic encryption epsilon is essentially a fully homomorphic encryption. So before introducing the details of bootstrapping technique, I want to introduce another encryption scheme called GSW. Now think about the simple question that how we do the scalar multiplication in ring LWE ciphertext is that I give a polynomial D times a ring LWE encryption of the message M. And we do naturally the scalar times vector multiplication, and this naturally returns an encryption of D times M. But the problem is that noise increases a lot. It increased by D times. So if the D is a big value, then noise is a huge one. And can we have a better scalar multiplication or homomorphic multiplication with a better control of the noise growth? The answer is yes. We can define a new extension of the ring LWE ciphertext as ring LWE prime, which defined as a number of ring LWE encryptions. We not only encrypt the message M itself, we also encrypt B times F and B squared times F up to B to the power K minus 1 times M. For simplicity, I denote this one as a vector of Ci, where each Ci is a ring LWE encryption. Now, to do the homomorphic multiplication, I first flatten the polynomial D into a vector D0 up to dk minus 1, where each element is a small value, not bigger than B over 2. And in some sense, the D is radix B converted in this formula. Now we do the homomorphic multiplications this way. I use the symbol O dot to denote the new homomorphic multiplication is that the polynomial D homomorphically multiply the ring LW prime ciphertext. Now, this homomorphically multiplication operation is essentially an inner product of the vector D0 up to dk minus 1 and the vector C0 up to ck minus 1. And it is easy to verify that this inner product will return a new ring LWE ciphertext of D times M. The advantage of this new ring LWE prime ciphertext is like the noise increase in this way is very limited, only by asymptotically logarithmic D times increase. Now we already learned how to do a very special homomorphic multiplication, is that homomorphic scalar multiplication. Now let's move on to construct GSW encryption for the standard homomorphic encryption. We can define the ring GSW encryption as a pair of ring LW prime encryption of two messages. One is minus s times m, and the other is the message m. In this way, now the homomorphic addition is straightforward. We're just doing the element-wise addition as the normal vector addition, and this naturally returns a ring GSW encryption of M0 plus M1. The difficulty here is how we define the ring GSW multiplication. And in this definition, the multiplication is somewhat asymmetric. Is that one input is a ring LWE ciphertext, the other input is a ring GSW encryption. And the output of the homomorphic multiplication is another ring LWE ciphertext. Now, we define the ring GSW multiplication using the symbol diamond as an inner product of the ring LWE ciphertext and the ring GSW ciphertext. And by doing some math, and this eventually returns a ring LWE encryption of M0 times M1. The biggest advantage for ring GSW encryption is like we can do the multiplication with much smaller overhead on the noise growth. And this gives us a better baseline to construct bootstrapping algorithm. Now let's make it clear that the problem that bootstrapping tries to solve. Now I give you an LWE sample. It's an LWE encryption of the message M, and inside this encryption we have a relatively large arrow called A prime. Now I want you to output using bootstrapping another LWE encryption of the same message, but inside this message the error term becomes relatively small. So now before introducing the bootstrapping, I need to introduce two very useful gadgets. One is called the accumulator, homomorphic accumulator. The symbol is like a plus and left arrow. And here ACC is a ring LW encryption. For example, the ring LW encryption of the message polynomial x to the power M0. So note here that the message is encoded in the exponent of x. Now the accumulation is essentially doing the ring GSW multiplication. In this way, we find that if we do the ring GSW encryption, we're actually doing addition homomorphically over the exponent of x. So we're actually doing addition of M0 plus M over the exponent of the polynomial. The second gadget is called the MSB extract. The idea is to try to homomorphically extract the most significant bits of the encrypted message. So the input is a ring LWE encryption of x to the power of m. Now after operation, I get a LWE encryption of the MSB of the M. And this can be implemented by it should be ring LWE encryption of M by a test polynomial and some other minor operations. Finally, we are able to talk about the details of bootstrapping algorithm. So remember, the intuition behind the bootstrapping algorithm is that we somehow to design the method to do the LWE decryption within the exponent of the ring element, essentially the exponent of x, the polynomial x to the power of m homomorphically. So a simplified version of the algorithm is like I first prepare some keys. Now it's called the evaluation key, EKI, equals and ring JSW encryption of x to the power of SI for the secret key S. Remember the LWE encryption secret key is a vector S. Now this evaluation key tries to encrypt every component of that secret key in the exponent of the ring element. Now we initialize the accumulator register called ACC to the x to the power of b. Now we perform a for loop. Inside the for loop, we try to accumulate uh, uh, the evaluation key to the accumulator register. So after the loop, we get a ring JSW encryption of x to the power of this red part. And remember, this red part essentially then LWE decryption. So finally, I perform the MSB extraction function to get the new LWE ciphertext with much smaller noise inside. So now I claim that this one is the algorithm that correctly returns another LWE encryption of the message M. The proof goes like this. We try to prove that in the for loop, this line, its execution actually gives me a ring LWE encryption of x to the power b minus AISI. Therefore, after the for loop terminates, actually get then ring LWE encryption of x to the power b minus some AISI. This one is equivalent to like scaling factor times m plus e. Now this homomorphic MSB extract algorithm brings out m out of this exponent and returns me the correct LWE encryption of the message M. Some computer scientists have concerns about the performance of FHE. So the question here is that the real performance of FHE is practical, or at least we can make some efforts to make it practical. Before I talk about the FHE performance, I want to discuss a very important preliminary about the polynomial. Is that how we represent a polynomial, fx. So a natural and straightforward representation is we use the coefficient as a vector called coefficient vector to represent the polynomial. And however, we can have another form of representation called sample vector. Think about the Lagrange interpolation. Is that I give you n distinct evaluation points of the polynomial as shown in this illustrating example. And the sampling theorem says if I give you n distinct samples, I can uniquely determine or recover the polynomial fx of degree n minus 1. So in other words, you can either use coefficients or the evaluation points to represent a polynomial. This is exactly what the entity technique is invented for. Remember in FHE schemes, all the operations, homomorphic operations, including bootstrapping, are boiled down to the basic polynomial multiplication over the ring. So why is ring setting very important? Because over the ring, we can do the so-called NTT, the number theoretic transform. The entity is defined as for a given omega, which is the primitive nth root of unity. If we evaluate the polynomial, for example, ax at the evaluation points, omega to the power k from 0 up to n minus 1. This omega to the power of k actually consists of n distinct roots of unity. So if we evaluate this polynomial at this these very special evaluating points and the sampling vector can be computed very fast in quasi-linear and log n time. And an interesting story about this n log n faster Fourier transform algorithm is the great mathematician Gauss already discovered this algorithm a long ago, but he never published his result. And 160 years later, in the 1970s, Cooney and Tukey reinvented this algorithm. Because of the entity technique and some other hardware acceleration techniques, the FHE performance is increasingly improved over the past few years. If we do not consider bootstrapping, the main performance bottleneck is the homomorphic multiplication, which can be done in 7.96 milliseconds on GPU. And due to the themed coding technique, which I didn't cover in this talk, one homomorphic multiplication is equivalent to about 65,000 homomorphic floating point multiplications. If computing this way, one encrypted floating point multiplication on GPU can be done in 1.2 times 10 to the minus 4 milliseconds. And note this value is gradually approaching the modern CPU performance for a normal and unencrypted floating point multiplication. However, if we consider bootstrapping, the bootstrapping is much slower than the homomorphic multiplication now, and is at least 2 orders of magnitude slower. And the best result on FPGA is like we can do bootstrapping in 187 milliseconds. So here the quick takeaways are, for multiplicative depth constraint tasks, without getting bootstrapping involved, then FHE is quite practical. But if you want the multiplicative depth to be unlimited, which suggests you need bootstrapping, then the FHE scheme is still not practical. So in the last section of my talk, I want to showcase some real-world applications where FHE techniques could be applied. The first good example is the private information retrieval. It is a very specific multi-party computation problem. Is that we have two parties here, Alice and Bob. Now Alice owns a secret index I, and now Alice tries to query Bob's database called DB and want to extract the ith item in the database without leaking the secret I. A straightforward solution is Alice just downloads Bob's entire database and query the database locally, which definitely eliminates the risk of leaking the secret value I. However, the problem is that it incurs large communication overhead, which is proportional to the size of Bob's database. So is it possible that we can achieve like a relatively small communication overhead while solving this problem? By introducing FHE, we can solve this problem this way. First of all, we view this database as a two-dimensional matrix, and we try to query the database by not one index, but two indices, ix, iy, which returns the ix row and iy's column of the database. And remember that this size of the indices is a logarithmic of the database. So now Alice just encrypts her indices ix, iy to Bob. Now Bob can homomorphically perform a so-called index expansion procedure that can expand Ix into a 0, 1 vector with the Ix item to be 1, whereas the other elements are 0. And likewise, we can also expand encryption of Iy to a 0, 1 vector with the Iy's element to be 1 and all the other elements to be 0. So in this example, Ix equals to 0, 1, 2, and I1 equals 0. Now we perform this vector matrix multiplication, and this, of course, returns me the Ix row, the element in the Ix row and Iy's column homomorphically. So by doing this, the communication overhead is reduced significantly. Just logarithmetic of the database instead of the linear size of the database shown in the previous slide. Another interesting example is the threshold private set intersection problem. So in the PSI problem, we have Alice and Bob, and Alice has a set called S, and then Bob has his own private set C. Now, the computational target is we try to compute the intersection of the set S and the set C. If and only if the intersection size satisfies some requirement in this figure, this requirement is like we hope the intersection size is bigger than a threshold value T. And the privacy requirement that we don't want to reveal anything else except the intersection itself. This threshold PSI would be very useful in applications like dating website because the basic logic of the dating website is the website tries to match a man with a woman based on how many interests they have in common. For example, they have the same favorite food, the same favorite movies, books. So if this the number of the commons exceeds some threshold value T, then the website thinks that it is a perfect match. However, the privacy concern here is the man and woman, if they don't have much in common, they don't want to reveal much about their individual interests. The threshold PSI protocol can be structured as the follows. We first use fully homomorphic encryption to design a threshold token generation protocol. At the end of the generation protocol, the client and the server has secret token K and K prime respectively. And the property here is that if the threshold requirement is satisfied, then K will be equal to K prime. Otherwise, they are two random numbers. And then after generating the two tokens, we augmented the original size by appending the token to the end of the element in the set. And after that, we perform a standard PSI to get the intersection. And this intersected result will be the desired output of the threshold PSI. FHE can also be applied in federated learning in the AI domain. So in this example, the cloud has a model and he distributes the model to Alice and Bob. After receiving the model, Alice and Bob trains the model locally, use his or her own data, denoted as data A and data B, to a local model. And after local training, Alice and Bob encrypt the model by his or her own secret key SKA or SKB and uploaded this model to the cloud. And cloud performs the so-called secure aggregation algorithm to aggregate the two separate individual models into a joint model under both keys SKA and SKB. Finally, the cloud performs a distributive decryption algorithm and extracts the model from this encrypted form. The last example is a very active research topic in the recent years called verifiable computation over encrypted data. In the standard FHE paradigm, the Alice encrypts her data X and sends it to Bob. Bob locally performs an evaluation procedure which returns an encrypted result Fx. However, it remains a problem that if Bob cannot be trusted and the result may be wrongly computed. How to solve this problem? The idea is that along with the evaluation procedure, Bob also generates a proof pi and sends the proof pi together with the encrypted result to Alice, and Alice can verify this proof by this verify algorithm. Alice will be convinced that Fx is correctly computed.
Finally, let me conclude this talk by highlighting several points. The first, the security of fully homomorphic encryption is built upon learning with error assumption and other related lattice problems. Second, the feature of FHE that supports a limited multiplicative tab is realized by Gentry's bootstrapping technique. The performance of FHE is indeed practical if we don't consider bootstrapping. And finally, the FHE can be applied in multi-party computation protocols. Well, it is mostly used as a communication reducing tool to achieve optimal communication overhead. This is the end of the video. Thank you for watching.